All right, students, this week we're going to start off with QA and QC of film. So you have several objectives that are listed here for you. You'll want to go through them and make sure that you understand each of those. So first thing we're going to talk about is sensitometry. So sensitometry measures response of film and exposure along with processing. So if we expose a step wedge, this is a step wedge, if we expose a step wedge, you can see the thinnest part is going to be dark and the thickest part is going to be lighter. So this is similar to air compared to bone. It's going to give you a graph, and we're going to talk about that graph. We're going to log it. So, sensitometry, accomplished by exposing and processing film, then it measures and evaluates resulting densities. So the purpose of sensitometry is the evaluation and maintenance of exposure factor systems. So we evaluation also of the intensifying screens and monitoring the processing equipment. So those are the reasons that we do it. We use a pedometer or a sensitometer. It's used to create uniform set of densities on film. So the densitometer provides measurement of light transmitted through the film. So it measures the optical density. So the sensitometer exposes the film, and the densitometer measures how dense each step is. The step wedge is used to monitor X-ray equipment, also used to monitor film screen combinations. It's not recommended for processor monitoring. There's a special thing that we do for the processor. So this is a sensitometer. It uses a controlled light source. It produces the same amount of light each time it is triggered. So you put the film in and you cover it and you hit expose, and it gives an optical step wedge. So this is a newer modern way. Instead of using a step wedge, we use an optical step wedge. So the sensitometer, it's available in 11 or 21 step variations. So the 11 step versions increase density by a factor of 2 for each step. The 21 step version increases the density by a factor of square root of 2, so 1.41 for each step. So the sensitometer, the digital system applications, so laser and dry imaging systems, picture archiving and communication systems, and calibration of flat panel monitors. So the densitometer, it's uniform light source and optical sensor. Its calibration controls allows for easy calibration. So each time you go to use it, so this is measuring the density on the film that was exposed to the sensitometer. So you're going to take each step and you're going to zero it out. You're going to calibrate it here with, and then it'll show you 0, 0, 0. You're going to stick the bar right under here and you're going to push it down. When you push it down, that actually the arm goes down just a little bit, and it goes ahead and it exposes and gives you a reading on what that density is on that film. So optical density numbers, so the formula is the optical density equals the log of 10 over I over I/O over IT. So if 100% of light is transmitted through the film, the optical density is 0. So there's no density on the film at all. So if none of light passes through the film, the optical density is 4. So that means it's completely black. So if the film is completely blue, light blue, like I said, we add the dye to it, then it is going to be 0. And if the light transmitted through is black, there's very little to no light, it's going to be an optical density of 4. So opacity is the ability of film to stop light transmission. So I won't make you calculate anything, I just wanted you to know that there was a formula. So the D and E curve, it describes the relationship between the density and the exposure. So D and E, density, exposure, done through sensitometry, and is also known as a sensitometric curve, characteristic curve, and the Hunter-Dryfield curve, so the H&D curve. So we usually talk about the H&D curve. Sensitometry's roots lie in analysis of photographic film. So you can see here, this is a typical H&D curve. It says the characteristics sensitometric curve graphically represents the relationship between varying X-ray exposures and image density. So here is your sensitometric curve, plots optical density. So against the linear relative exposure. So you have your log relative exposure, and it allows a large range of exposures displayed in few numbers. So here's the density, and here's your log exposure, and you can see here the different points that were measured. Okay, so 4 would be totally black, and 0 means nothing. So this is your H&D curve. So reads on a scale from 0 to 4. Like we said, 0 means all light is transmitted, 4 means no light is transmitted. The typical diagnostic densities are between 0.25 and 2.5. Those are the two ranges that we like to be in between. Parts of the curve. So there's base plus fog. So the toe is the density minimum, where the density becomes light. So that's the minimum that you're going to see on the film. The straight portion is used to demonstrate the relationship of to film exposure versus density transmitted. So the shoulder is D max, density max. It's where the density becomes the darkest. Base density. So it's inherent in a piece of film due to dyes and etc. It's usually around 0.1 optical density. So fog density is inadvertent exposure during storage, handling, in the darkroom too long. So fog density should not exceed 0.2 optical density. Base plus fog. You cannot separate the base and the fog density measurements. Typical range of optical density for base plus fog. So you have 0.18 to 0.23, should not exceed 0.25. So the toe is your D minimum. It's controlled by phenidone. You don't really need to know the chemical, just know that it's in the developer. So the toe is usually in the developer. It's fast-acting reducing agent in the developer. It produces gray tones on the film. We used to have to know the chemicals within developer and fixer. You don't have to know that now. So the straight line portion, it's the area of the curve between the toe and the shoulder. It contains ranges of useful densities. So typically 0.25 to 2.5 or 3.0. 3.0 is getting kind of dark, but 2.5 is the range, the top range that we like. So the shoulder is your Dmax, is controlled by hydroquinone. So it's slow acting reducing agent of the developer. You don't need to know that. It produces the black on the image. So you can just say that the Dmax is the developer and it produces the black on the image. So your H&D curve, you can see here, we have all the different spots from the sensitometer where we can measure and see the difference between each. So film characteristics, we have resolution, speed, contrast, and latitude. And the resolution is the ability to accurately image an object, also known as detail, sharpness, definition, resolving power. And it's inversely related to the size of the silver halide crystals, which we talked about last week. So the speed is the ability of the image receptor to respond to low exposure measures. It's sensitivity or speed. So the speed index specified by 1 plus base plus fog. So here's your speed. So you have film A and you have film B. So this is the minimum here and this is the maximum here. So we're just about at 4. So here's where the speed is 1.5 and then you're at about a 2. So faster film will have a curve closer to the y-axis of the graph. So film sensitivity is affected by the size of silver halide crystals, the number of sensitivity specks, and the thickness of the emulsion. All the above directly related to film speed. So affected by processing. So it is also affected by immersion time, solution temperature, and chemical activity. As you look at the curve here, you can see how the speed changes with each. So the steeper the slope, the faster the speed. You can also see here, here's gradient with time and temperature right in the middle, and you've got speed and you've got fog. I'm not going to go too much into this. As you can see, the different temperatures of the chemicals do have to do with the speed. So this is the log relative exposure, and you can see that the time and the temperature does make a difference on the speed of the film. So contrast controlled by hydroquinone establishes the shoulder, thus affects the slope of the straight line portion of the curve. And the film contrast and curve. The film contrast defined by straight line portion of the characteristic curve, so the gamma slope of the straight line. So if we have film A and film B, this is a higher contrast film. It's steeper than this one. See how the slope is just kind of gradually going? This one, it jumps up, the density jumps up, so it's more contrasty. So as the line becomes more vertical, contrast gets higher. Think of that sensitometer and what that looks like. So average gradient, used to identify contrast of film by manufacturers. Slope of the line is drawn between optical density. So 0.25 plus base plus fog plus 2.5 plus base plus fog. So you can see here the average gradient is here. So we take the base plus fog, 0.25 plus base plus fog, and then 2.5 plus base plus fog, and then you can get your gradient in there. So higher the average gradient, higher the contrast. Your latitude, so lower the slope, more horizontal the line, the wider the latitude. So more horizontal the line, the wider the latitude. So a lower scale in film, more latitude. So if we're looking here, what are we dealing with here? So the film here is a very high contrast film that has a definite toe and shoulder. You can see here we're just kind of coming in, and look how high we're going in optical density. So this is really steep also. This is a wide latitude film here. So we'll talk about this in class also. So we talk about all the different ones here between A through D. If you can be able to identify each one, that would be awesome. All right, that has to do with your QA and QC. And like I said, we're going to cover these graphs a little bit more while we're in class.